Alright, here we go. Yeah. Alright, so this is what you would have ended up with your experiment after you've done some subtraction of like crucible and lid and all that stuff, right? So you would have ended up with two values from your experimental data. So to get to the empirical formula of magnesium to oxygen in magnesium oxide, we have to get some data from there. So like Ruben said, we can do a simple calculation. If we had 0.2 grams of magnesium and we ended up with 0.3 grams of magnesium oxide, the first calculation we can make is the mass of oxygen, okay, not O2, the mass of oxygen atoms that attached was 0.1 grams. Is it okay? All right. Now that you have that, everything we've done in calculating empirical formula is ready to go. So if I'm just setting it up like in this table kind of form, I like it to do it like that because for me, everything is where it's supposed to be and I can see it and it makes sense. So Mg to O, in terms of mass, is 0.2 to 0.1, and I'll write mass there so I know what those numbers represent. Empirical formula or any formula is done in mole ratio, so this is not ready to go yet because if you just left it like that, you would have 2 to 1. So no. We're going to convert it to moles. How do we do that? Well, N equals M over big M tells us that to find out number of moles, and we know mass, we need to divide by molar mass. So Mg divided by 24.31. I don't know either, I'm just guessing. Cool. Divided by 16. If you're like, how do I know that? It's because I've done it lots of times. Not because like I sat home and did a Kahoot on the periodic table. This here then is going to get you moles, right? So 0.2 divided by 24.31 is a number. I said this last time. I should carry a calculator with me to do this.
You should stay strapped and always.
You be quiet.
Obviously not, as kids.
0.2, 20. Alright. 0.008. Okay. First lesson in how much you should round. You should round to the number of significant figures in the value that you've been working with that has the least amount of significant figures. So what that means is if you weighed stuff to 2 decimal places, the maximum number of significant figures you can round something to is 2. Because even though we are using values from the periodic table that have 4 significant figures, you have to deal with the least amount of accuracy that's available to you. And because you only measured mass in 2 decimals, or 2 significant figures in this case, because that's what you're left with. So I'm going to round that to that. 0.01 divided by 16 is 0.0063. Okay.
It's not 0.0.
Huh?
It's not 0.0.
What did I do? Oh, another 0. Wait, what? 0.1 divided by 16. 0.062.
You just said 0.0.
Oh, did I? My bad. I'm sorry, Ruben. I've ruined everything. What's the step that we do here when calculating empirical formula? We divide by the smallest value to both. So I'm going to divide both of these to get the proportion.
What's his molar mass?
Yes, sir. That's okay. We all trip out from time to time.
You got something to tell us now?
That's a story for later.
Oh, awesome.
All right. This here, 1.30 to 1. I just divided both of those numbers by the smallest number. Remember that when we did it on Monday? Yeah. Because it's the smallest. Alright.
Like each go up slightly.
Make sure you get that picture.
So that's the zero we use.
That's the empirical formula.
Yeah, but is that
Based on your experimental data.
just ours?
A made up one of 0.2 grams and 0.3 grams.
Right. So what does that